In this video, we discuss MATLAB built-in functions for solving initial value problems. Now, earlier in this lecture, we discussed demos of basic implementations of explicit Euler, implicit Euler, modified Euler, and also I think by yourself you could easily implement something like midpoint or Runge-Kutta 4, as this is, well, rather straightforward extension of these implementations of Euler methods that I demonstrated. However, MATLAB also contains quite a suite of ODE solvers with a lot of bells and whistles, such that you can use them for when you are encountered with a initial value problem that you want to solve in an accurate and reliable manner. And these ODE solvers, well, they contain features such as automatic error control, adaptive step selection, which will choose this step H based on characteristics of the numerical solution, but also variable order methods, which kind of outweigh computational cost versus numerical accuracy. Now, these different solvers all have the same syntax in order to call them. And they can be called as follows. So the output of all these methods, well, this will contain the solution vectors, where the first component of this output is the independent variable, so x or time or whatever. And note that this is not necessarily equidistantly spaced, because all these methods, they do their own time step selection. Unless you tell them explicitly to take a specific time step, they will optimize the time step and do adaptive stepping. And the second output, well, that's then your numerical approximation of the function y that satisfies your ODE or your IVP. How to call them? Well, they have different names. I will go into that in a minute. The arguments that you have to give are a function handle, which computes the right-hand side of your ordinary differential equation, or the derivative of the function y that you want to approximate. You have to give a span for x, which is a two-element vector with the starting point and the end point, and you have to provide an initial condition over here. You can set additional options also if you want to do so. For instance, that you want a specific tolerance or a specific error when you're looking at very high accuracy problems. But usually the standard options here are more than adequate in order to solve your IVP. And now let's take a look at the different kinds of solvers that are provided within MATLAB. Now, your first method of choice should always be ODE 4.5. Now, for non-stiff problems, this is probably all you need. What this does is it combines a fourth and fifth order Runge-Kutta methods that does automatic error detection and adapts the time step or the x step, so this h parameter, based on these characteristics or gradients of the solution. So I would always first go to use ODE 4.5 whenever you're encountered with a problem. Now, we also saw in the previous video that sometimes these explicit methods, we saw it for explicit Euler, but it also holds for explicit Runge-Kutta, that explicit methods can get really quite into trouble when encountering stiff equations. And for stiff equations, there's also quite a lot of other solvers. I think a good choice here to try is probably the ODE 23TB, which uses, as it is said, an implicit method, which is somewhat more, let's say, somewhat more resistant to these stability restrictions in stiff equations. And that's an implicit Runge-Kutta method as well. So these Runge-Kutta methods really are very nice for solving your IVPs. But here you have a suite of solvers that also contain some multi-step methods, which we didn't cover in detail here, but also have their specific advantages and disadvantages. To close off, let's look at some examples for how to apply these built-in solvers to specific problems. So if we look at our general example, the one we've used many times in this lecture, the differential equation dy dx is x times y with an initial condition y at x is 0 is 1. And we want to integrate from x is 0 up until x is 2. Well, we can easily call then our, let's say, standard time integrator ODE 45, or standard IVP integrator, I should say, to be more precise. So we use ODE 45. Well, we supply here a function handle which computes this right-hand side of the ODE. We specify the span in x that we want to compute, and we close off with the initial condition so that y at x is 0 should be equal to 1. So just calling this will return a vector x, a vector y, and I plotted them here so that we have the exact solution, and I believe it's e to the power x squared over 2, as well as the numerical solution of ODE 45. And you see that they fit, at least on this plot, qualitatively virtually perfectly. So that's our general example. Let's take a look at the stiff equation. This stiff equation that we saw in the previous video, where we have a very fast component in the solution corresponding to this minus 1000 times y, but we also had a very slowly evolving component of the solution corresponding to the cosine part of the solution. Initial condition y is 0, x, here we only integrate from 0 to 0.2. So I define here the function as follows. So that's simply standard MATLAB syntax. We say that f is a function of x and y, and here we simply plug in what is here on the right hand side. And I integrate this using both a standard explicit time integrator, or IVP integrator, let's say, ODE 45, as well as a specifically oriented towards stiff problems integrator ODE 23TB, which is an implicit Runge-Kutta ODE solver. And also I plot them here, and we see that in order to cover a distance in x from 0 to 0.2, ODE 45 had to take 285 steps, whereas our specific stiff systems integrator only had to take 34 steps. So that's much more suited to solve such stiff equations. And you can actually check. What I would do in this case is, well, you just use ODE 45 out of the box for your system. And then when you see, well, it's performing subpar, so it's taking very, very many steps in what seems to be a very smooth region of the solution, then that's a very key takeaway, that you have a stiff system or a stiff ordinary differential equation, and then you should try these stiff integrators. So whenever ODE 45 gets into trouble, check if your equation is stiff. That would be my general advice here. But these solvers can also really easily be used for solving systems of ordinary differential equations, and as we've seen in the lecture also, a generalization to systems from an algorithmic point of view really doesn't involve a lot of changes to your code or to your solver. And here I considered the predator-prey or Lotka-Volterra equations, as they are called, where x is the amount of prey, y is the amount of predators in the system, and I just put in some conditions over here, some parameters, alpha, beta, delta, and gamma. And we start out from 10 predators and 10 prey, and we integrate from 0 to 100. So what you do is, well, the main challenge here is to define this function f, which is a vector. So we have a system of equations. So f is a vector. It's a function of time and of the solution, y. and then you just write it as you would when you convert such a system to a vector. So this right-hand side, well, that's alpha times the first component of the unknown minus beta times the first component of the unknown times the second component of the unknown, and analogous for the second equation. Then we can simply call it using ODE 45, and out comes then a vector t and a matrix y, where this has two components, both in this case x, the amount of prey, and y, the amount of predators.